Good morning, everyone. Today I will continue the course about quantum trajectories, but today I think we'll do less quantum trajectories and more stuff related to the proof that we will do a bit later. So today my aim to give just a reminder of quick methods we can use for Markov chains on finite space. And then I will start to introduce the theory of quasi-compact operators. So first, let's go back to Markov chains. For this, I will introduce every property for matrices that are positive. So just give all the definition. So we say that A is positive if every definition of A is positive. And we say that A is strictly positive if all the coefficients should be positive. The following I will denote by sigma A the spectrum of A. And the spectral radius of A will be the maximum of the modulus of the eigenvalues of A. Okay. So now with this definition, I will speak about the primitivity and the reducibility of matrix, because it's very essential when you are studying the Markov chain, because usually our matrix transition will be, well, every time it will be positive and sometimes it will be reducible and sometimes even primitive. And based on the property of A, we'll be able to get some limit theorems. So, another definition for A, we say A is zero for every N, so there exists an K integer such that K power of A and AJ is should be positive. So here's only for one AJ. And then we say that A is primitive if there exists some wave. Integer so that A to power K is strictly positive. But here the difference it's true for every AJ, and here it's maybe not the right case. We have some example of irreducible matrices that are not primitive. Okay. Now the two last definition I need to start to speak of Markov chain are the simple eigenvalue and the dominating eigenvalue. So we say that an eigenvalue is simple. If the dimension of the kernel of A minus N is equal to 1, and we say that an eigenvalue is dominating or if for every alpha in the spectrum of A different of lambda of alpha, which is a spectral gap. So that means if I do a drawing here we have the modulus of lambda, and everyone is in this cycle for every other spectral value, eigenvalues of my matrix A.
Excuse me, in the previous definition, we really want just the kernel to be trivial, or you can algebraically.
Yes.
Okay, you allow this.
Yes.
Okay, thank you.
Yeah. Okay. So now let's think of Markov chains on a finite state. So we will consider a finite place. And we say that P is a solution matrix so it's equal to x, I, x, and I if for every x and I pair of E without the xi is positive. And secondly, we want that for every x with E, the sum on y of the x-y is equal to 1. So here we have indeed a positive matrix. We call it stochastic. So now our Markov chains is actually the information of the Markov chain is entirely in this P, and that means that if we have more information about P, we can have more information about the Markov chains. Everything is hidden in this P. So first, okay. If I evolve my, if I'm starting like let's E, an initial distribution of B. So we want to know, okay, what is the evolution of my Markov chain? Does it converge to some final probability equation? Does it have some invariant measure? So we don't know about that. So first, you define what is the invariant measure. So we say that phi as an invariant measure is A pi, yes, pi, if pi p is equal to pi. So I just will define what is phi of p of y. Here, phi of y is a sum on x of pi of x against p of x1. And so if we have for every y, p of y equal to p of y, we say that we have an invariant measure. Okay. Now, let's talk about the periodicity of a Markov chain. For this, before giving a description, let's take some one example. Say, for example, we have a two-state Markov chain. Here, we the easy Markov chains. So we go to two by with probability one, and we go to from two to one with probability one. So here that means that we just do some cycles, and with every two steps we go to one, every two steps we go to two. But we could have like more difficult Markov chain. You want to know, okay, will I go back to some states after some time? And so we can define this with the definition of periodicity. So we take some state in D, and we define the following quantity. So dx will be the great common divisor of all this time. I will go back to and I will go back to x, which is called the period of x, called the period of x. And if my great common divisor is equal to 1, we will say that my x is that period. So if p of x is equal to 1, we will say x is the period. Here we define the periodicity of one It's a great common divisor.
Oh,
yes, it's sorry, yes. Maybe okay. So now the question is, can we define the period of a Markov chain? So the answer is yes, but we need some assumptions that is related about the assumption we made on the matrices before, which is the following. So it's the irreducibility assumption, which is very close to what we had about the matrices, meaning that we say that the Markov chain is irreducible. If for every x, y, e, there exists an instance such that e at the power n of x, y is strictly positive. So it is exactly what we defined for the irreducibility of the matrix. And so now, under this assumption, because now with this assumption, we know that for every x and y, so we can just put xx, we are able to get at least one n, which at least one n in this set, so we can define the x. So if it was not the case, we would not have this definition. So if the Markov chain is irreducible, so we have the following, but not more like a question. All the states have same period. And we call G the common period, the period of all states. And it is the period of the Markov chain. And if G equal 1, as before, we say that the Markov chain is a period. Okay. So now the last small assumption I want to talk about is something which is very close to irreducibility, but something called phi irreducibility for Markov chain. And why I want to talk about this, because if I go back to quantum trajectories, the Markov chain we are studying in the context of quantum trajectories does not, the assumption of irreducibility does not hold, and so we cannot use everything linked to irreducibility. So what is the irreducibility? So it's quite close to the irreducibility we defined here, but here that means that there exists a measure phi of B such that for every A in E such that P of A is strictly positive, then for every X in E, we have the existence of M and N star such that we can go after sometimes in my set A. So here, this assumption depends on a measure phi, which is on my set set of states B. And so, like I said, yes, this assumption is not verified in the case of quantum trajectory. So every techniques using the theory of disability won't be we won't be able to apply this kind of techniques based on this definition.
Your E is finite, right?
Yes, E is finite, but you can
Yeah, okay, so but does it mean that it's bicyclic singletons?
Yes. Okay. Here for this case here I don't go I just choose the easiest settings. Okay. So now I will present you like one of the most known theorem when we are studying Markov chains, which is the theorem of Frobenius. And it says the following thing. So we take some primitive matrix that are the real and primitive matrix. So what we call is the following. So the spectral radius of A will be strictly positive. Moreover, it will be a simple eigenvalue of A. And finally, we have the following thing that rho of A will also be a dominating eigenvalue. So we will have a spectral gap. And there exists a unique vector B positive such that so A of B will be equal as for A of B. And the norm of B will be equal to 1. So what does it mean for a Markov chain? That means that if I take a Markov chain with a primitive transition matrix, then since I know that the spectral radius of my primitive matrix for a Markov chain will be equal to 1, that means that 1 will be a simple eigenvalue dominating, simple dominating eigenvalue of my transition matrix. And moreover, since I have this vector, I will also know that I will have the uniqueness and the existence of some probability measure, invariant probability measure for my Markov chain. And everything is based actually on this Frobenius, and the only thing I need is the fact that I want a primitive matrix for my Markov chain transition. Okay, So I just yes.
Because here you don't claim convergence, but my impression that you do have convergence here, right?
Here
you have permittivity.
Here I just have the existence of dominating eigenvalue, which is the spectral energy of A. For the moment, I don't have any convergence. I just have the existence. Okay. However, now, if I'm so the color is for Markov chain. Up. So let Markov chain for the matrix B. If is primitive, then there exists a unique priority priority. And for every distribution on E under some sense mu of E at the power n which converge to P infinity. So how does it work? So I won't do the whole proof, but the idea of the proof is that we will be able to decomposite P at the power n. That means if I take P, I know that one is eigenvalue, and I know that okay, I have an eigenvector which is my invariant measure. So that means that P will be equal to 1 multiplied by some projection, so I will call it maybe, well, let's just call it P infinity, but we looked at it was a projection to this vector, plus some n, which is just something will be negligible. So here in n, we know that of n will be strictly smaller than 1. So I mean that when I will iterate my my P at the power n, so here it doesn't change anything, because here we have just the projection and the projection will be the same. So here we still keep the projection towards P infinity. However, here, like with this decomposition, we have n5 like n equals 0. So actually, when you multiply them, it will be something equal to 0. And here, we just have this, some n at the power n, But we know that the spectral radius of n is stricter, smaller than 1. So that means that in a long time, the power of P will behave like just the projection towards the invariant measure. So that means that even if I take any probability measure here, at the end, based on this decomposition of P, I will get the convergence for the probability, the invariant measure. So here I think I will just keep it like this because in the following, when I will talk about the proof, but everything about the quasi-compactness and stuff like that, I will do a complete proof on how does it work. But here the idea is really, okay, if we want to remind something is I have this decomposition for my matrix P. So let's just remind this because it will be very useful when do the generalization of this kind of yes.
I just want to be sure that I understand everything correctly. Because you mentioned simplicity, that would be simplicity of there's only one eigenvector, right?
Yes.
But do you allow to have generalized eigenvector when you take a minus lambda squared or to cube equals 0 and so on? This was my question in your previous definition about simplicity. You said that lambda is a simple eigenvalue if the kernel has a dimension 1.
Yes.
But let's take the Jordan block, right? You have one.
Yes.
I mean, is that simple eigenvalue for you or not? You have now one on the diagonal and something else on the just above the diagonal and 0 everywhere else. Is that eigenvalue 1 simple for you or not? Just to be sure that
yes.
Yeah, but then you cannot try for that one, that composition, right? Because
no, here I just want a single I just want.
Yeah.
But I have only one vector, which is
okay.
It's what I mean here.
Okay. So okay, that's it.
But we see a bit. I think maybe later we'll have something related to what you say because we'll have several dominating eigenvalues in the future.
Right. Okay. So let's discuss it later. Yeah.
Okay. Okay. So we have this, and now I just want to show you also some ideas about how proving a central limit theorems for Markov chains based on this decomposition. So it's more like prove a central limit theorem for Markov chains. So, if I want to prove some central limit theorem, so we will have to find some process. So, we will again take example real sum. So, for some f, we consider the sum from 1 to n of f of xk. Here is the evolution of an Markov chain. And my goal is to get a CLT for this. So, if I want a central limit theorem, a good idea is to look at the characteristic function. So, okay, I will look at my characteristic function. And actually, my goal is to write it like this. So, here mu will be my initial distribution. I want to write it as a perturbation of P evaluated at the function 1. So here, this one is a function called. So now, if I want to study this static expression, I need to find some good way to define my P of t. So we need to find a good derivation of the matrix Q. So some T would be T. And now we know one thing. We know that P, we can decompose it like this. So if P is equal to 1 multiplied by some corrector plus some n, which is negligible compared to this, I want, okay, if I take some t close to 0, so the goal is to get some P of t, which will be some lambda of t multiplied by some, it won't be the projection towards P infinity, so it will be some P of t plus some n of t. So actually, here, I have some function, which are function from t to an eigenvector, t to some matrix, and I will have like 3 different perturbation of my objects. So here,
It may be complex, right? It's not a real matrix.
yes. It could be complex. Here it just at the end we'll take it real, but we can also take some z in C and take an holomorphic perturbation.
No, I mean that the first line that defines your matrix on the right hand side. On the same equality on the right hand side. So
here,
on the right.
Here.
Yes. This is your.
Yes. PT could be complex. Yeah, it could be complex. Yes. PT it's like, yes, it's T. PT is well, we will take it holomorph. No. Function we take some interval centers in 0 to the space of complex matrices. Okay. And so now we can use the perturbation theory of Kato. So if my Kato perturbation theory so if P repeating the analytic and P admits a simple dominated eigenvalue, then there exists an analytic function on some A point intended to be such that the function will be t to lambda t, t to p of t, and t to n of t. And we want that p of t will be equal to lambda t pt plus n of t. And now, yes. What does it mean? That means that we kept the decomposition of the matrix. And so when I want to compute the power of n, actually we will keep the fact that p of t and n of t, when you multiply, we will still have like n. Here, p of t. So when you take p of n as the power n, it will be lambda of t as the power n, some projection towards p plus n at the power n, and still we have the spectral radius of rho, which will be smaller, slightly smaller than the modulus of rho. So we still have the spectral radius of n of t, which is strictly smaller than the modulus of. So that means we still have a simple dominating eigenvalue for all maturation close to 0. So is it okay or?
What is this E1? It is just.
Yes, it's just some interval included in I.
So it can be very small around 0.
It could be very small. I just need something very small into 0. It could be as small as I want. Because at the end, for the moment we have t, but when we want the central limit theorem, we will divide by square root of n. So for n large enough, will be in I1. So for I don't care about the length of I1. I just want the existence. Is it okay? So now, let us finish that. So we have like, if I want my, so as I said, we had the square root of n here. And so it will be equal to mu of, I will just put it in here, it will be p of n of t now applied to 1. And then we have mu of, if I take back everything here, lambda n of t sort of n of p of 1 plus n of. So this is not important because it compared to this, it's negligible. And actually, what we see here is that in a long time, this will be, I do it with the equivalence. We won't do every Taylor extension, but it will be equivalent to my lambda n of t divided by the square root of n. So if I able to give a good Taylor expansion of lambda, then it will be finished because it will converge to this. And so indeed, so I won't do the proof because it will take a lot of time, but actually we have that lambda of t is equal to 1 minus some sigma square divided by 2 is square plus some something negligible related to t squared. And if I replace here everything by t on the end, we have at lambda of t divided by square root of n will be I minus t squared divided by n. And if I take it at the power n, we see that it will converge to the exponentials of is the 2 here. It will converge to the exponential of minus square of sigma t square of 2. And we recognize by using the Levy theorem that we have the convergence law towards the normal zero. So we have that Sn of f. Once that's the law of n, converging law n 0 square root of sigma. So here is the idea behind how to get a central limit theorem. I know that there are a lot of different proofs to get this kind of limit theorems from Markov chains, but I wanted just to explain this because it's how we will do it for quantum trajectories. Of course, what are the issues between the case of finite space and the case of quantum trajectories is, of course, we are not living at first in a finite space. Secondly, so we don't have this matrix. So P. How can I decompose it like this? Two good questions. Like I did it because I had a spectral gap on finite dimension. It's quite easy. But for my operator pi I don't have any idea of how to get it. So actually, there is an answer to this question. And the answer to this question is what we call quasi-compact operator. And so my goal now is to present you what are quasi-compact operator, what kind of properties they have, and how can we adapt everything we did here on finite space to quasi-compact operator acting on some space that we will define later. Okay? So now my goal is to introduce you to quasi-compact operator. And so it will be some functional analysis. For it, I will just define some definition. So here we take B, it will be a Manor space. The L of B will describe the space of bounded linear maps on B. If I take some T, in this space, I will define the operator norm of T, which is the increment of C of F. So yes, we use some norm. So we define the operator norm like this, and at the end, I will define the spectral radius of T, and I will define it with the Gelfand formula. So it will be the limit when n goes to infinity to the operator norm of T at the power n here, and with second lemma, it will be actually equal to the infimum of the sequence. So here is now second lemma. But, okay. We have everything to start to talk about quasi-compact operators. So, then we take some two bounded operator on B. And so we say the quasi-compact operator the advanced. So we want that A plus B is equal to B. We want that F and G are invariant by Q. We want that F is finite dimensional. And that all the eigenvalues of Q. So here with this, I just mean it will be restricted to F. So Q restricted to F are modulus the spectral radius of and then I just want that the spectral radius of Q this time restricted to H is slightly smaller than O of Q. Okay? So we want F and G in some direct, both invariant by Q. This one is finite, but this one has all the greatest spectral values of Q. So it means that everything which happens in G, which is infinite, a priori, it's not important because everything will have will be contained in this F, which is finite dimensional. And so that's why you can see that, okay, if I'm looking at a quasi-compact operator, in long time, it will behave as a matrix. Why? Because in long time, my Q will mostly act only on a finite dimensional space. So everything I did with matrices should be able to do it on quasi-compact operator. So my goal is to show you how it is possible to indeed get this intuition of being able to do everything on this. So first, I will just do a small drawing about representing the spectrum of this kind of operators, and made an analogy with the compact operator. So what does it say here is F is finite and all the eigenvalues have modulus of Q. So that means here I have of Q and I have some eigenvalues. I rewrite I want on the cycle, but I have a finite number. And everything else is here. And here I have my spectral graph. So the comparison with compact operator is the following, because if you had a compact operator, you have at most a countable compact operator. The spectrum is at most countable. Fine. The only accumulation point is a zero. It's zero. So that means that if I do sort drawing here, actually you will have a convergence sequence of a value converging to zero. And of course, so it should start here. You can say that, okay, I will have this, and then this, and then everything will be here. So when you have a compact operator, of course, it is a quasi-compact operator. But you don't have the reciprocity. Of course, if you are quasi-compact, you don't have a compact operator. So I won't enter more in the details, but people who are studying this kind of operators in the algebraic point of view, actually they construct quasi-compact operator with some quotienting by the compact operator to get some stuff. But I'm not an expert on this, so I won't talk everything about this. But there is another point of view of the quasi-compact operator linked with this compact operator. Okay. Okay. So now, the first example. We take some Q acting on some banner space, and our goal is to show, by using the definition, that it is quasi-compact. So let's try it. So here, we take B will be all the Lipschitz function of the interval 0, 1, and we will undo so Lip of 0, 1 is undo with the norm I will call it just double bar F, which will be the step norm plus the constant of Lipschitz. Norm. And here the Lipschitz constant. Okay. And so now we define the following operator. So Q of F. Let's define it. Q acting on Lip 0, 1, such that for every F in Lip and X in 0, 1, will have Q of F of X will be 1 over 2 of this field. Okay. So here we see 0, 1 as more like R or divided by Z. If I go higher than 1, I go back to 0. So it's just So here we define, we do not split by nu, the Lebesgue measure on P. And what we want is, okay, I remind that, okay, I just want the decomposition of Lip of 0, 1 with some good properties. So here, what we have is the following thing, is that Lip of 0, 1 is equal actually to the linear span of the function equal to 1, so all the constant, plus all the functions in Lip such that the Lebesgue measure of F is equal to 0. So it's quite fast forward to series, and to have the decomposition, it's just take some F and you write it like this, F minus the Lebesgue measure of F plus the measure, and this is in this, and this is in this, and you have the decomposition. So we have a good decomposition. So our question is, okay, does this decomposition is the decomposition I want for my quasi-compact operator? So first, we can show that what we call this S plus Lip we show that f and g are invariant by Q. So here it's also a directly computation. You can show the invariance by Q. And now what we want is, okay, here we look at it, it's a finite dimensional, and since Q of 1 is equal to 1, we know that the spectral radius of Q is greater than 1. Okay, so let's us point out that Q of 1 is equal to 1, and then spectral radius of Q is indeed greater than 1. Is okay. So that means that we need to show that the spectral radius of Q restricted to G is strictly smaller than 1. And if I'm able to do this, I will have everything. So let's go. We take some f and g. Listen, forgot to say so I take some f and g. Since u of f is equal to 0, and I know that my function is going to the complex, I want that, okay, for sure, I will have some x in 0, 1, such that the real part of f of x1 will be equal to 0, and same for the imaginary part. So there exists x1 and x2 with 0, 1, such that the real part of x for x1 is equal to the imaginary part of f of x2 is equal to 0. Because if you know the case, by positivity as integral will be something which is not equal to 0. So that means that if I look at f of x, it is equal to f of x minus f, so here, real part of f minus real part of f x1 plus e imaginary part of f of x minus imaginary part of f of x2. So I can read it like this, and that means that if I'm looking at f of x, okay, for every x, that means that here will be smaller than 2 times the Lipschitz constant of f. Why? Because you get it here with the real part, you get it here for the imaginary part. So at the end, we have that f of x is smaller than 2 by the constant. And that means that we have the supremum norm, which is every time smaller than 2 the Lipschitz function of f. Okay? So it means that if I will relate it here, that means something because we had this relation, And that means that actually M of F is a norm on this space equivalent to G. So at the end, M of F is a norm equivalent to this class. And that means that if I want to compute the spectral radius related to this norm, I just have to compute the spectral radius related to the constant function. And so it is to compute the spectral radius for M. And by direct computation, we have that for every n integer, Q F is smaller than 2 to the power minus n to f. And when we take the definition of the spectral radius, it implies that O of 2 of G is smaller than 2 to the power minus 1, so equal to 1 over 2, which is strictly smaller than 1. And then at the end, we have been able to prove that Q is a quasi-compact operator with this decomposition. So here, it required a lot of work to get the quasi-compact operator. And actually, if I give you an operator and you want to prove that you have some invariant subspace that have some properties, it's like here we had some luck because it's very actually direct in the pole and we are able to do everything like this. But in general, it's very hard to show such a decomposition. So my goal now is to give you another way, which is more direct, to prove the quasi-compactness of an operator. And for this, I need just to introduce a new kind of quasi-compact operator. For the moment, we just looked at quasi-compact operator, but there are special quasi-compact operator, which are very interesting to study. So let's talk now about diagonal type quasi-compact operator. Okay. So we take some quasi-compact operator. Quasi-compact operator. And remember, we have Q and F and Q and G, and Q and F is acting on a finite space. So we can say, okay, Q and F is acting as a matrix. We can say, okay, maybe we can diagonalize this matrix. So actually, we have this. So Q restricted to F is diagonalizable if and only if we have this relation that if we're looking at the operator norm of Q of n divided by the power of spectral radius, so this finite. And if it's the case, then we say that Q dot diagonal phi. So now, if I have some Q that I can diagonalize on F, I'm able to give a good decomposition as I show earlier for the case of matrices. So decomposition of the quasi-compact operator of diagonal phi. So if I have such an operator, actually there exists some lambda k on first I n étoile, some lambda k in CP, some projector K, and that, and sorry, and also the linear operator. Such that, well, the following thing we want that if K here is equal to a Dirac K of L of pk. So that means that everything is equal to 0 except when we have pk and lpk. So here is for every k and l, we want p. We want that pkn is equal to npk is equal to 0 for every k to 1 p. And if we have everything like this, we can actually write Q of n, which will be the sum for k to 1 to p. Here we have our lambda k at the power n as before, multiplied by my projector towards the eigenvector eigenvector associated to my eigenvalues here, plus some n at the power n. And moreover, for every k in 1p, we'll have the modulus of rho k is equal to the spectral radius of rho q, and of course rho of n is smaller than rho q as before. So now we have been able for this kind of operator to decompose it as the matrix we had earlier for the Markov. So now we have this sum with p different eigenvalues. Something here which is negligible. And so when you look at it in a long time, everything will behave as this sum. Okay. Okay. So now let's speak about a very good theorem to show that operator are quasi-compact without knowing everything about space, but more about the properties of the operator. So it's a theorem by Ionescu to Serra-Marinescu. Yeah, Marinescu. So it was in 1915, and it has been a bit generalized by Loïc Hervé and Hubert Lignon in 2001. And by the way, just to talk a bit about these two persons. So they have a really great book about quasi-compactness and everything related to limit theorems of Markov chains based on the quasi-compactness. So most of the stuff I'm telling today is based on their book. So I really recommend to look at their book. A lot of great stuff. So now let's talk about this theorem. So the setup is the same as before. We take some balanced space with some norm. We take Q, a linear bounded map on B. And here we have some semi-norm, so it's not necessary. It's not. So we take a semi-norm, but usually in every proof it will be an over-norm on Q, but just take a semi-norm. And so, if we have 3 points, so the first point is the following. We want that if I look at Q of F in B, that the norm is smaller than equal to 1, I want this relatively compact compact in B, but standard with the semi-norm. So here it's this norm. Secondly, I want that there exists some M such that if I'm looking at the semi-norm of Q of F, I want that it's smaller than this constant for every F in B. So if I want just to do a small comment about this assumption, usually when you are looking at a Markov operator, your continuous semi-norm will be the subprime norm. So almost every time it will be, and it's something very easy to verify. However, here, which is actually hard assumption, we want this. We want that there exists some n, an integer, and or some positive number such that for every f in B, yeah, we want this inequality. So here we look at the norm of Q at the power n of f. It's smaller at R multiplied by my continuous summing norm plus small r at the power n f. But here, this R needs to verify an equality. So we want that R is strictly smaller than the spectral radius of Q. Let us do some comments about this equality. So this equality is called Dublin-Fortet inequality, which is very useful in all the world of dynamical system and Markov chains. And let us remark that here is just the existence of one n. You don't need it for every n. You don't need it for n great enough. It's just you need one n. So you just have the existence of this n. So it is usually you will get it for every n, but if you get it, for example, for n equal to 1, everything is fine because you have everything. And so when you have all these three assumptions, then you have that Q is quasi-compact. On your space. So we transform everything about finding a good decomposition into verifying three assumptions only on Q. For this one, the first one, you see that there is a question of relative compacity. So most of the time, everything here, you will get this assumption by applying Arzellas-Colli theorem. So this kind of assumption is not so hard to prove. It's usually just an application of Ascoli theorem. And as I said, for Markov chains, it's almost immediate, so it's not very hard. However, this one is the hardest, and we'll see later when we talk about how we proved the quasi-compactness for quantum trajectories, that it requires a lot of work. But for the moment, let's take back an example for special 2 to see how does it work, how can we prove such for every assumption. So we go back to the example of before. So I will take back my leap of 0, 1 with my ellipsis norm. And this time we have Q of f of x, which we equal as the following. So f of x2 w x2 plus f of x plus 1 wx plus 1 divided by 2. So where w is the Lipschitz function, non-negative, and such that Wx2 plus Wx plus 1 over 2 is equal to 1 for every x in 0, 1. So just take this kind of operator. Error call is to prove that this Q is that this Q is quasi-compact. Let's just show that if we take W is equal to 1 divided by 2, it's actually the same example as before. It's just a generalization of the previous example. So we want to prove that it's quasi-compact. So we want to prove 1, 2, and 3. So if I want to prove 2, so we start with 2. We just want to prove that Q of F, oh, sorry, and here's this term, it will be the supreme number. We want to prove, okay, that Q of F infinity is smaller than a certain constant by F. So let's X in, let F in B and X in 0, 1. So we have 2 of F of X, which is equal to F of 2 double X plus F of X plus 1 divided by 2 double X plus 1 divided by 2. And so here by triangular inequality, we get that this is smaller than the supranoun F, this is supranoun F, and so we have supranoun F Ws plus 2 because it's non-negative, so I can keep it like this, plus supranoun Wx plus 1 plus 2. And here, since this plus this is equal to 1, so actually we are smaller than this, and then for every F in B, we have 2 of F infinity, which is smaller than N infinity. And this, we get the second iter. Now, we try to get the 1 and the 3 together. So we want to prove this kind of equality. So we need to get it for n equal 1. Here we don't have to go higher than n equal 1. So for n equal 1, let us estimate n of Q1. Okay, so let's go. Let x and y in figure 1. We have Q of f of x, and it's Q of f of y, which is equal to this minus this plus the same thing but with the plus 1. So since we have the plus 1 here, we want to, okay, we know that F and W are Lipschitz. So when we have the product of two Lipschitz, we want to say, okay, one we will estimate by the supreme norm, and the one by the Lipschitz norm, and vice versa. So here, what we can say is, okay, I can say I'm equal to f x plus 2 of w the x plus 2 minus w y2. But I just added it, so I have to remove it after. So here, it's this. And here, then I have to add it back, and I have plus w y over 2 of f x plus 2 minus f 1. So it's just to have some f in here and some w here. And so here we get that if I want to estimate this, so here I will have fx2 minus f infinity. Here we have the distance between x and y divided by 2 mw, so it's like mw distance of x and y divided by 2, plus, if I look at this, we have w y of 2, and we have m of f divided by 2. And if I did the same with x plus 1, so I will have the same here, and here for the m of the distance of x and y. I will have the same thing here. So for the first one, it doesn't change. But still we have w, the y plus 1 over 2, m of x plus 2, distance of x and y. And when we sum everything, what we get is that m of q of f is smaller than, here we have it 2 times, so it's just 2, it's just f infinity minus w. And here we only get this because here it's equal to 1, so we just have m of f divided by 2. And so we get that my Lipschitz constant of q of f is smaller than something which only depends of w, which is not related to q. Here we have m of f of 2, and then we have this infinity norm. Okay? And so now we just have to add to get the whole norm of f, the infinity norm. And so we just proved earlier that q of f infinity is smaller than f infinity. So that means that if I'm looking at q of f, here, it's smaller than 1 plus minus w plus, so here, multiplied by f infinity plus mf divided by 2. And here it's finished. Why? Because m of f is smaller than the norm of f divided by 2. So here we have 4 is equal to 1 plus mw, small r, which is equal to 1 divided by 2. And since q of 1 is equal to 1, we know that rho q is smaller than 1, and that means that rho is smaller than rho q. So for n equal to 1 or equal to 1 plus the constant norm of W and or is equal to 1/2, then we get the Dublin-Fortet inequality and it gives its matrix. And to obtain item 1, we show that the Q of we show that Q of F will be such that F smaller than 1 is a bonding subset of E of E. And by Arnaud-Colli, we get the relative capacity. So here, I just want to point out that, okay, it's indeed way more easier than using the definition. However, what we can see here is, okay, this Dublin-Fortet inequality here it works very well. We had a good way to do it, but in general, it requires a lot of work and to get the good estimations.
Yes. But is it easy to get a function satisfying that condition that omega x over 2 plus omega x plus 1 over 2 is equal to 1, apart from this constant 1/2?
Is it easy?
Yeah. Well, if you look at not worry, just like curiosity. I was thinking if it is.
That's a good question, actually. I think I will think about it. But it's. We have maybe enough time to talk about the last part. Okay. So now.
Maybe for the example, isn't the 10th function on 0, 1 an example? You take the piecewise affine, it's 2x on 0, 1/2, and then 2
absolutely. Yeah, indeed.
That's, I guess, the simplest one except the constant function.
Yeah, thank you. Indeed.
Okay. So now, the next part of today is, okay, we saw everything with a matrix. And so now we want to do the same, but for a quasi-compact operator. So the goal is, okay, now I know to prove how to prove Q is a quasi-compact operator by some theorem. I know that if I have a diagonal type quasi-compact operator, I have a good decomposition. So now I want to know, okay, same for the matrix, if I have a good way to perturb my quasi-compact operator, do I keep this kind of decomposition? Because if I can keep this decomposition, everything I did for the matrices, I will be able to do it for my quasi-compact operator. Okay? So it's the goal. It's to do the same. So first, let's talk about dominating eigenvalues. So we say that Q has S dominating eigenvalues. So if you can decompose to add F plus H, X plus G, as usual. We want that Q of F is indeed in F. We want that Q of G is included in G as before, and we want, okay, but the dimension of F equal to S to have the S eigenvalue, and Q positive to F as S simple eigenvalues. So it's exactly what we want to get this concept of S single eigenvalues, and actually our quasi-compact operator will have this S dominating eigenvalues. Okay. So now let's talk about the perturbations. So here I will define for every M integer, P of M and for every I interval of R, Tm of E of L of B is the set of M differentiable functions from I to L. And the interval we'll be interested in will be the interval centered in zero. So for the rest of the course, we will consider interval centered in zero. Okay, so as before, my goal is I want to have some perturbation smoothly enough, so I can take C1, C2, C3, etc. until C infinity. And I want to perturb my operator P. So let's just assume that there exists a collection of operators E or T I that into Qt is in some CM I bonded linear operators of P. So if Qt equals 0 is equal to n Q has S simple dominating eigenvalue, quasi-compact, then there exists against some I1 included in I such that for every T in I1, Qt is quasi compact and has n dominating eigenvalue. That means that for T small enough, if I have these two assumptions, I will keep my decomposition of the quasi-compactness. So it's exactly the same as for the matrices here. We'll be able to, if I want to get, for instance, the central limit theorem, I'll be able to give a good decomposition of Qt divided by square root of n, and I will be able by, okay, here we have some Cm, so my eigenvalues will be also function m differentiable. The same for all my projectors, the same for the part which is negligible. But if here my perturbation is analytic, then again all my eigenvalues, my S simple dominating values will be analytic related to T. All my projector will be analytic to T, and all my negligible part will also be analytic in T. So we keep the smoothness of the function when we perturb our operator Q. And it will be very useful to study actually the power of n, because we keep with good decomposition. But to illustrate this, let's go back to Markov chains. So, some global space. Urbana space. And we have some Excel Markov chain. Of kernel 2. We take from F real value functions. And as before, I want to get a central limit theorem for S and F in B K of L of F of X. So what will I do is the following. So maybe I will call it G. C of F. So we'll define some Qt of F, which will be the Q of EIT of G. So here, just take this new, and this will be my perturbation of so T to Qt is analytic in some sense. And Q for 0 is equal to Q. So now it's as before. If I'm looking, so X new is this initial distribution of my Markov chain. Then we'll have the following thing, that the expression of mu of my characteristic function will be exactly equal to rho t at the power n of 1. And now we are back to the initial problem of, okay, am I able to give a good decomposition of Qt, and how does it work? So now, if I know that Q is quasi-compact, then we will have the good decomposition. If Q quasi-compact of diagonal type, compact of diagonal type, then Q from k from 1 to f to some lambda k k plus n. And we have that Qt will be equal to the same thing, k to 1 to some s, lambda k of t, pk of t, plus n of t, and with Qt at the power n, that will be to the power n of my lambda q, and since we have lambda n smaller than lambda q, everything here also will vanish, and everything here will only depends on how evolves how behave the eigenvalue of Q. And so now the goal is, okay, as before, we want to give a good Taylor expansion of my eigenvalues, and then I will be able to derive again the central limit theorem for my Markov chains. So I think for today I will stop this, and I think next time I will go back again to control trajectories and show you how to use this theory and some interesting results about the quantum trajectories.
Just one question.
Yes.
The function Qt it is EITSNG, right? It's not G, it's SNG.
Here?
No, the line below.
Here?
Yeah. ITSNG or just G. Just to get the same expressions in the bottom. In the exponent.
Here?
Yeah. It is G or SNG?
G.
Yeah, okay. But then how you get that
If
ITSN?
when you do some the computation of SN, when you compute the Q of t.
Okay.
Because here, oh yes, here is SNG, yes, so sorry. What is it? Here is the GS.
Okay, but it's the same symbol Qt or?
Yes, here it should be the same, but applied to the one.
Any other questions? Are there any questions online?
I don't think so.
Because the previous one is not the.
Yes, it's the previous one.
Okay, so if there are no questions, well, someone is saying something, or maybe not. Yeah. Okay, so if there are no questions, then we'll stop here, and we'll meet again tomorrow at 9 in the morning.
Thank you.
Thank you. Thank you. Bye.